October 1909, Cincinnati, Ohio. The Cincinnati Shaper Company's factory floor echoed with the rhythmic clang of a machine that would outlive every critic who dismissed it. A massive cast-iron shaper weighing 4,200 pounds sat crated for shipment to a locomotive works in Pennsylvania. Its ram traveled 36 inches with each stroke, driven by a gear-driven mechanism that machinists already considered obsolete. Modern milling machines promised faster cutting, smoother finishes, and continuous rotation instead of the shaper's back-and-forth reciprocating motion. Engineering journals published articles declaring shapers a transitional technology, soon to be replaced by rotary cutters that could machine complex surfaces without the vibration and noise that made shaper operation unpleasant. The fundamental criticism seemed irrefutable. A shaper's cutting tool only worked during the forward stroke, with the return stroke wasting time and energy. Mills, by contrast, cut continuously as their rotating spindles engaged the workpiece without interruption. Time studies showed mills could remove metal 40 to 60% faster than shapers for most common jobs, making them obviously superior for factories prioritizing production efficiency. William Hendricks stood in the Cincinnati factory's shipping department that October morning, watching workers bolt the crated shaper onto a flat car. He'd spent 15 years as a pattern maker before transitioning to machine tool sales, giving him practical knowledge that contradicted the engineering consensus dismissing shapers as outdated technology. The machine's design embodied principles that high-speed milling couldn't replicate. The cast-iron base weighed over 1,000 pounds alone, providing mass that absorbed cutting forces mills couldn't handle. The ram's reciprocating motion generated forces perpendicular to the workpiece, pushing down rather than sideways, creating rigidity advantages invisible in speed comparisons but critical for certain applications. Yet factory managers across American industry were making purchasing decisions based purely on production rates. The new Bridgeport mills could hold tighter tolerances on small parts. Cincinnati Milling Machine Company's universal mills could cut gears, splines, and complex contours that required multiple shaper setups. Brown & Sharp's production mills delivered consistent results with less skilled operators, reducing labor costs in the shops facing perpetual workforce shortages. The mathematics of machine tool economics appeared straightforward. A mill costing $200 that could complete jobs 50% faster than a $900 shaper would pay for itself within months through increased throughput. Factories building automobiles, agricultural equipment, and industrial machinery needed production volume, not the plodding, methodical cutting that shapers provided. The shaper's reputation suffered further from its operational characteristics. The machine was loud, with each ram stroke producing a distinct clang as the cutting tool engaged hardened steel. The reciprocating motion created vibration that rattled adjacent equipment and fatigued operators during long shifts. The intermittent cutting action required more frequent tool sharpening than continuous mill operations, adding maintenance costs that efficiency experts duly noted in their recommendations against shaper purchases. But in locomotive works, shipyards, and heavy equipment manufacturers, certain jobs exposed limitations in mill technology that wouldn't become apparent until those faster, quieter, more modern machines tried cutting hardened steel components that shapers handled routinely. By 1912, American machine shops had embraced milling technology with enthusiasm that bordered on religious fervor. The Cincinnati Milling Machine Company's production doubled between 1908 and 1913, driven by automobile manufacturers who needed thousands of engine blocks, transmission housings, and chassis components machined to precise specifications that hand methods couldn't achieve economically. Frederick Taylor's scientific management principles swept through American industry, bringing time studies, standardized operations, and relentless focus on eliminating wasted motion. Shop foremen armed with stopwatches measured every machine operation, comparing actual performance against theoretical maximums that engineers calculated from cutting speeds, feed rates, and material properties. Shapers performed poorly in these efficiency analyses. A typical facing operation on a cast-iron surface might require 18 minutes with a shaper, completing the cut through repeated ram strokes that advanced incrementally across the workpiece. The same operation on a horizontal mill could finish in 11 minutes, with the rotating cutter removing material continuously rather than intermittently. Machine tool salesmen capitalized on these comparisons, demonstrating mill superiority through carefully selected test cuts that highlighted speed advantages while avoiding the specialized applications where shapers excelled. Trade magazines published articles with titles like "Modern Milling Replaces Obsolete Shaping" and "The Last Days of Reciprocating Cutters," creating industry consensus that shaper technology had reached its evolutionary dead end. Apprentice machinists entering the trade after 1910 received limited shaper training, with shop instructors focusing on mill operation, lathe work, and emerging grinding technologies. The message was clear. Shapers represented the past, mills embodied the future, and ambitious machinists should develop skills relevant to modern manufacturing rather than wasting time on machines the industry was abandoning. James Mitchell operated a job shop in Cleveland that served local manufacturers needing custom parts and prototype work. He'd purchased a new Cincinnati No. 3 mill in 1911. Attracted by its ability to cut gears and perform complex milling operations his previous equipment couldn't handle. The mill justified its cost within 8 months through increased job capacity and faster turnaround times that attracted customers willing to pay premium prices for quick delivery. Yet Mitchell kept his 1909 shaper operational despite pressure from his accountant to sell it and recover floor space for more productive equipment. The machine occupied 80 square feet that could accommodate 2 modern drill presses or a second mill that would generate more billable hours. Equipment maintenance records showed the shaper required more frequent attention than newer machines, with its mechanical drive system demanding regular lubrication and adjustment that newer hydraulic equipment eliminated. The shaper's survival in Mitchell's shop depended on occasional jobs that other machines simply couldn't complete: large keyways and locomotive drive shafts, heavy flats on marine engine components, and internal surfaces and slotted forgings that mills couldn't reach effectively. These jobs arrived irregularly, perhaps once monthly, but they paid well because few shops maintained equipment capable of handling them. By 1915, shaper manufacturers faced collapsing demand that threatened their survival. Cincinnati Shaper Company's production dropped 60% from its 1908 peak. Smaller manufacturers like Rockford Shapers and Atlas Machine Works discontinued shaper lines entirely, focusing on lathes and specialized equipment that still attracted buyers. The industrial consensus appeared settled. Shapers were obsolete machines waiting for retirement. Spring 1917 brought America into World War I, and with it came manufacturing challenges that exposed critical limitations in mill-based machining. Military contracts demanded components from hardened steel, materials that could withstand battlefield stresses, but resisted conventional cutting with ferocity that destroyed mill cutters and stalled production schedules. Artillery breech mechanisms required slots and flats machined into heat-treated steel with Rockwell hardness exceeding 45 HRC. Armor plate contracts specified keyways cut into hardened surfaces that would secure drive mechanisms in naval gun turrets. Tank transmissions needed internal splines machined from forgings that had been hardened to prevent battlefield failures. Mills approached these materials through rotating cutters that engaged the hardened surface tangentially, creating side forces that deflected lightweight mill spindles and caused catastrophic cutter failures. Tool life dropped precipitously, with carbide-tipped mills lasting minutes rather than hours when cutting hardened steel. The continuous cutting action that made mills efficient for soft materials became a liability when confronting hardness that generated tremendous heat and stress at the cutting edge. Robert Crane managed machining operations at a Cleveland factory that had contracted to produce 15,000 artillery breech mechanisms for the U.S. Army Ordnance Department. The specifications seemed straightforward. Machine a 6-inch keyway into hardened steel forgings, maintaining tolerances within 0.05 inches across the keyway's length. His shop had 3 modern mills, recently purchased equipment that handled every other contract job efficiently. The mills failed completely on hardened breech forgings. Cutting attempts generated sparks, horrible screeching, and broken cutters that cost $15 each to replace. Even at conservative feed rates and minimal depth of cut, the rotating mills couldn't maintain purchase on hardened surfaces without deflecting or chattering violently. After destroying $200 worth of tooling and completing exactly 0 acceptable parts, Crane faced contract default that would bankrupt his operation. The solution came from an unexpected source: the 1909 shaper that Crane had relegated to a corner of his shop, covered with canvas and used primarily as a workbench for storing toolboxes. His oldest machinist, a German immigrant named Karl Hoffmann, suggested trying the shaper for the keyway operation, arguing that its ram-driven cutter would push straight down into the hardened steel rather than deflecting sideways like mill cutters. Hoffmann's logic proved correct. The shaper's massive ram, weighing over 80 pounds, delivered cutting forces perpendicular to the work surface with momentum that carbide-tipped mills couldn't match. The reciprocating motion allowed the cutter to disengage completely during the return stroke, preventing heat buildup that destroyed mill cutters through continuous contact. Most importantly, the shaper's cast iron frame absorbed vibration that would have shaken lighter mills apart during aggressive cuts into hardened material. The first breech mechanism required 90 minutes to complete, far slower than theoretical mill operation. But it was a completed part that met military specifications, something the modern mills hadn't achieved after days of attempts. More importantly, the shaper's cutting tool remained sharp after completing the keyway, showing minimal wear compared to the destroyed mill cutters that littered Crane's shop floor. Word spread quickly through Cleveland's manufacturing community. The obsolete machine nobody wanted had solved a problem that modern equipment couldn't handle. The shaper's unexpected success with hardened steel demanded an explanation that went beyond anecdotal evidence. Engineers at Cincinnati Shaper Company, sensing potential market revival, conducted systematic testing that quantified why their 1909 design outperformed modern mills on specific applications that wartime production made critically important. The fundamental advantage stemmed from force vectors that machining textbooks had dismissed as irrelevant during the mill revolution. A shaper's ram moved horizontally, but its cutting tool engaged the workpiece at an angle that directed primary forces downward into the massive cast iron table. This geometry created a compression loading condition where the machine's 4,200-pound weight worked as an asset, providing resistance against cutting forces that would deflect lighter equipment. Mills, by contrast, generated side-loading forces as their rotating cutters engaged material tangentially. These lateral forces created bending moments in the mill's spindle, column, and base that increased proportionally with cutting resistance. Hardened steel generated enormous resistance, creating deflections that destroyed dimensional accuracy and produced chatter marks that ruined surface finishes. Testing at Cleveland's Case School of Applied Science revealed the magnitude of these differences. A horizontal mill-cutting hardened steel at 60 feet per minute generated lateral forces exceeding 800 pounds, causing measurable spindle deflection of 0.012 inches at the cutter tip. The 1909 shaper, cutting the same material at 40 feet per minute, generated downward forces of 1,100 pounds, but produced table deflection of only 0.002 inches due to its compression loading geometry and massive construction. The reciprocating cutting action provided additional advantages that continuous milling couldn't replicate. Each shaper stroke allowed the cutting tool to fully disengage from the workpiece during return travel, giving the cutter edge time to cool between cuts. This intermittent contact reduced heat accumulation that softened carbide tools and caused premature failure. Laboratory measurements showed cutting-edge temperatures of 650 degrees Celsius during shaper operation compared to 900 degrees during continuous milling, a difference that doubled tool life even when cutting abrasive hardened steel. The shaper's mechanical simplicity contributed to its reliability under brutal cutting conditions. The ram drive system used a slotted link mechanism with a 3-inch diameter steel pin riding in a bronze-slotted block. This simple design could transmit tremendous forces without the complex gear trains and hydraulic systems that modern mills required. When cutting forces spiked unexpectedly, the shaper's mechanical drive simply absorbed the shock through elastic deformation of its heavy components rather than failing catastrophically like delicate mill gearing. Tool geometry also favored shaper operation when machining difficult materials. Shaper cutters could be ground with larger relief angles and heavier shanks than mill cutters required. The larger relief angles reduced friction and heat generation, while heavier shanks resisted deflection that caused dimensional errors. These advantages became critical when cutting keyways, flats, and other features where form accuracy mattered more than surface finish. The engineering analysis revealed an uncomfortable truth that challenged decades of manufacturing orthodoxy. The shaper wasn't obsolete technology replaced by superior mills, but rather specialized equipment optimized for applications that mills handled poorly. The industry had abandoned shapers not because mills were universally better, but because most applications didn't require the shaper's unique capabilities. Wartime manufacturing of hardened military components exposed this oversight with consequences that threatened contract fulfillment across American industry. By autumn 1917, machine shops across the industrial Northeast faced a peculiar equipment crisis. Shapers that managers had been trying to sell or scrap for years suddenly became the most valuable machines in their facilities. Factories with operational shapers could bid on lucrative military contracts that competitors with mill-only operations couldn't touch. The U.S. Navy's Bureau of Ordnance required 50,000 breech mechanisms for 5-inch deck guns, each requiring multiple keyways and flats machined into heat-treated steel components. Existing suppliers using modern milling equipment were missing delivery schedules by months, creating bottlenecks that threatened naval construction programs. Contract officers began specifying that bidding shops must demonstrate shaper capacity before receiving awards, effectively excluding facilities that had fully embraced mill technology. Equipment prices reflected this dramatic reversal. Used 1909 Cincinnati shapers that sold for $200 in 1915 commanded $800 by late 1917, with buyers competing desperately for machines that had been considered worthless scrap 2 years earlier. Shops fortunate enough to own operational shapers suddenly possessed competitive advantages that translated directly into profitability during the greatest manufacturing boom in American history. James Mitchell's Cleveland shop exemplified this transformation. The shaper he'd kept operational despite pressure to remove it now ran 3 shifts daily, cutting keyways and flats for naval contracts that paid premium rates. Mitchell hired 3 additional machinists specifically to operate the shaper continuously, with each shift producing 15 breech mechanisms worth $12 apiece to his bottom line. The machine his accountant had called a liability generated more profit in 3 months than his modern mills earned in a year. Cincinnati Shaper Company resumed production after a 3-year hiatus, but manufacturing capacity couldn't meet demand from shops desperately seeking equipment that could handle military contracts. The company's order backlog extended 12 months by spring 1918, with customers willing to pay 4% premiums for immediate delivery. Other manufacturers re-entered the shaper market, but wartime material shortages made rapid production expansion impossible. The shaper's renewed prominence sparked technical innovations that improved performance for hardened steel applications. Tool manufacturers developed new carbide formulations optimized for the intermittent cutting action that shaper operation provided. Cooling system improvements allowed shops to direct cutting fluid precisely at the tool workpiece interface, further extending tool life and improving surface finishes. Fixture manufacturers created specialized vices and clamps that leveraged the shaper's downward cutting forces to hold workpieces more securely than mill fixtures could achieve. Training programs that had abandoned shaper instruction hastily reinstated it. Recognizing that machinist competency now required familiarity with equipment the industry had prematurely declared obsolete, apprentices who had never operated shapers received crash courses from retired machinists who remembered techniques from pre-mill decades. Trade schools purchased used shapers to supplement curricula that had focused exclusively on modern milling technology. The wartime experience fundamentally challenged assumptions about technological progress that had dominated American manufacturing for 2 decades. Newer didn't automatically mean better. Faster didn't always translate to more capable. Sometimes solving specific problems required specialized tools that general-purpose machines couldn't replace, regardless of their theoretical superiority in controlled test conditions. The 1909 shaper, mocked and dismissed, had proved its value when confronted with real-world challenges that exposed the limitations of equipment that had supposedly made it obsolete. The armistice in November 1918 brought predictions that shapers would return to obsolescence once military demand for hardened steel components disappeared. Manufacturing consultants advised shops to liquidate their shapers while wartime premiums still commanded high prices, arguing that peacetime production would restore mill supremacy for conventional machining operations. The prediction proved partially correct. Shaper demand collapsed as military contracts ended and factories returned to commercial production of automobiles, appliances, and industrial equipment that didn't require the shaper's specialized capabilities. Cincinnati Shaper Company's order backlog evaporated within months, forcing layoffs and production cutbacks that mirrored the pre-war decline. Yet shapers didn't disappear. Certain industries discovered that the wartime experience had revealed capabilities relevant beyond military applications. Heavy equipment manufacturers building mining machinery, oil field equipment, and marine propulsion systems required occasional machining of large forgings that mills still handled poorly. Die makers cutting hardened tool steel found shapers indispensable for creating punch and die components that stamping operations demanded in ever larger sizes. Robert Crane's Cleveland operation maintained continuous shaper utilization throughout the 1920s and 1930s, serving a niche market that valued capability over speed. His shop specialized in jobs other facilities rejected: oversized keyways, internal slots and hardened components, and heavy flats that required removal of substantial material from difficult-to-machine surfaces. The work arrived irregularly, but it paid premium rates that justified maintaining equipment and expertise that most competitors had abandoned. The next technological challenge emerged in the 1960s with numerical control machining. Computer-controlled mills promised precision and repeatability that manual operation couldn't achieve, combined with programming flexibility that eliminated setup time for complex geometries. Early adopters invested heavily in CNC equipment, convinced that computer control would finally render all manual machines, including shapers, completely obsolete. CNC mills indeed revolutionized manufacturing for complex components requiring multiple operations and tight tolerances across intricate surfaces. Aerospace manufacturers, medical device producers, and precision instrument makers adopted CNC technology enthusiastically, achieving production efficiencies and quality levels impossible with manual equipment. But CNC mills still cut metal through rotating spindles that generated lateral forces. The computer control was remarkable, the programming sophisticated, the positioning accurate, but the fundamental mechanics remained unchanged from manual mills. When CNC equipment encountered hardened steel forgings requiring heavy material removal, the same deflection and chatter problems emerged that had plagued mills since 1909. A 1987 study by the National Institute of Standards and Technology compared cutting forces and deflection between CNC mills and manual shapers when machining hardened D2 tool steel. The results surprised engineers who assumed modern CNC equipment would demonstrate clear superiority. CNC mills using carbide tooling and optimized programming achieved material removal rates 85% higher than shapers, but experienced spindle deflection 3 times greater and tool wear rates 4 times higher. The shaper, plodding and obsolete by every modern metric, produced flatter surfaces with better dimensional accuracy despite taking longer to complete each cut. The conclusion was inescapable. CNC technology added control precision but couldn't overcome fundamental mechanical limitations inherent in rotary cutting. For specific applications involving hardened materials and heavy cuts, the 1909 shaper's brutally simple reciprocating design still outperformed equipment that had supposedly made it obsolete 8 decades earlier. Today, functioning 1909 Cincinnati shapers remain operational in specialized machine shops, tool and die facilities, and restoration operations that value capability over modernity. These machines, now over a century old, continue performing tasks that modern CNC equipment handles poorly or can't accomplish economically despite exponential advances in control technology, materials science, and cutting tool development. The shaper's survival contradicts fundamental assumptions about technological progress that dominate contemporary manufacturing philosophy. Industries typically embrace newer equipment and abandon older technology based on straightforward economic calculations. Modern machines offer higher productivity, better precision, and lower operating costs than equipment they replace. This pattern holds true across virtually every manufacturing sector, making the shaper's persistence genuinely anomalous. Yet certain physical realities transcend technological advancement. Cutting hardened steel requires force that must be absorbed structurally. The 1909 shaper's 4,200-pound cast iron frame provides mass that modern equipment can't replicate economically. Contemporary machine tools prioritize lightweight construction for rapid positioning and reduced power consumption, design choices that make perfect sense for most applications but prove disadvantageous when brute force matters more than speed. The reciprocating cutting action, dismissed as inefficient for a century, offers genuine advantages that continuous rotary cutting can't match when machining difficult materials. The intermittent engagement allows cooling between cuts, reduces heat buildup, and permits cutting tool geometries that would fail under continuous loading. These benefits become critical when machining hardened steels, exotic alloys, and other materials that challenge even the best modern carbide and ceramic tooling. Machine shops that maintain operational shapers occupy a profitable niche, serving customers who've learned that not every job suits modern equipment. A Midwest tool and die maker recently completed a project cutting keyways in 300 hardened shaft blanks, each requiring a 12-inch keyway machined to 0.003-inch tolerances. Modern CNC mills quoted 8 to 12 weeks delivery with costs exceeding $15,000 for tooling alone. The shop completed the entire job in 3 weeks using their 1909 shaper, charging $8,000 and earning customer loyalty that generates repeat business modern competitors can't capture. The engineering lesson extends beyond machining technology to fundamental questions about how industries evaluate capability. Speed, precision, and automation dominate contemporary manufacturing metrics, creating blind spots where specialized older equipment outperforms modern alternatives for specific applications. The 1909 shaper succeeded not by competing with mills on speed, but by offering capabilities that rotary cutting fundamentally couldn't match regardless of technological sophistication. Perhaps most remarkably, the shaper's story continues evolving. A growing community of machinists, engineers, and manufacturing historians now recognizes that dismissing the shaper as obsolete reflected incomplete understanding of machining physics rather than comprehensive technological assessment. Trade schools are reintroducing shaper operation, acknowledging that comprehensive machinist training requires familiarity with tools that excel at tasks modern equipment handles poorly. The machine that machinists mocked in 1909, that factories tried retiring in 1915, that consultants declared finished in 1920, and that CNC technology supposedly replaced in 1970 remains valuable in 2024. Sometimes the oldest technology proves the best technology, not through nostalgia or tradition, but through simple physics that even a century of innovation can't overcome.